A good application of exponential functions is simple interest. So let's look at this case where you deposit $1,000 into a savings account that offers 2% simple interest. The question is, how much money will be in the account at the end of 3 years? Well, this is good practical knowledge for you to have. So let's assume that we put $1,000 into the account, and if we want to calculate 2% interest, we do times 0.02. In other words, we can't just multiply by 2%. We have to convert the percent to a decimal. Now let's go see what happens when we do this. Let's go ahead and cancel this out. We get 1,000 times 0.02. That gives me $20. Now, right off the bat, we can see that there's something wrong with this. This couldn't be well, for one, we're calculating the amount of interest that we would have at the end of 1 year, not 3 years. But the other thing is, there's no way, the question is how much money will be in the account at the end of 3 years? Well, this doesn't tell us the amount of money that we have in the account at the end of 1 year. It's 2% interest, but this is just the interest. It doesn't include the original amount, which, by the way, the original amount is known as principal. All right, so anyways, we'll get back to that and we'll write that down in a little bit. So if we want to get the amount in the account at the end of 1 year, then we have to add this plus, we have to add the initial amount plus the interest. So the way we do that is like such. Let's use a different color just because we can. So we take the initial amount and we add the amount of interest. And that is technically how we end up with the amount that we're going to have at the end of the first year. So plus this, remember that was the amount, we got the $20. So this is, let me correct that. Plus $20. So 1,000 plus 20 gets us 1020. That's the amount at the end of the first year. So again, this amount is called the end of the first year balance, and balance is the technical term for what you have left over in the account. So let's see what happens during the second year. In the second year, we have $1,020, and we have to add that to 1,020 times 0.02. In other words, we now get paid a 2% interest on what we had in the account at the end of the first year. So this will be the end of the second year. So let's see what that is. So that gets us 1020 times 0.02. That's 20.4. And so let's go ahead and write that out. So we get 1020 plus 20.4, and that'll get us 1040.4, and that'll be the end of second year balance. And then finally, let's see what happens if we want to find the amount that will be in the account at the end of 3 years. So we take the 1040.4 and 40 cents, of course, plus 1040.4 times 0.02. Let's see what that is on the calculator. 1040.4 times 0.02 equals $20, and let's round it to 81 cents. So $20.81, and let's go ahead and I'll go ahead and write that down. Plus $20.81, and let's use the calculator to double check and see what that is. Plus 1040.4 equals, so that's 1061.21. Whew. I don't know about you, but that felt like a workout to me to do all this work to get this result. So hopefully you are expecting that we are going to try to find an easier way. One of the things that I'd like to point out to you folks is this. When we look at this first calculation for the balance at the end of year 1, we see there's 1,000 here and 1,000 here. And I don't know if you folks recall, but way back when we talked about something called the GCF, or the greatest common factor. And what we said was, when dealing with polynomials, anytime you can factor out the GCF, do it. And the rule still applies here. So I'm going to go ahead and take that 1,000 and factor it out, and what's left over is 1 plus 0.02. So already I've had to write a little bit less than before, and I should still get the same result. Oh, I'm going to simplify it a little bit more even. I'm going to use PEMDAS. Remember, PEMDAS says simplify everything in parentheses before you multiply or divide. Parentheses are first on the list. So this is really the same as 1,000 times 1.02. Remember 1 plus 0.02? Let's just double check and see if we all agree. 1 plus 0.02 equals 1.02. All right. Then we multiply that times 1,000. And sure enough, we get the 1020 that we had before. So it seems to me like this is a bit easier than this, and especially if we have to do it multiple times. So now we'll go ahead and do it multiple times. We'll go ahead and we'll take the 1020 and multiply it by 1.02. And let's see what we get. Times 1.02 and 1040.4. That's what we got before. Yay. 40.4. So this looks like it's working. And we'll do it again. 1040.4 times 1.02. Let's try that on the calculator. Times 1.02. Gets us 1061.21. That's what we had before. 1061.81. Yay! This actually works. Now, I think I've told you folks before that one of the reasons we study algebra is not to make our life more difficult. The goal is to make our life easier. And so I'm gonna show you that even this that we just did could be easier. And one way to make this even easier is to try something like this. We could take the original 1,000 and multiply by 1.02, and then just take that result and multiply it by 1.02, and then take that result and then multiply it by 1.02. In other words, I didn't have to keep writing the end balance for each year. And just to double check, let's see if that actually works. So we take the 1000 times 1.02 times 1.02 times 1.02, and sure enough we get the 1061.21. Yay! Did I say 81 over here? Let's double check. It is, sure enough, it's 21. Let's write that as 21. Anyways, this system seems to work, and it's way easier than the method that we started with. And just for the heck of it, just for giggles, we're going to make it even a little bit easier, and we're going to do it in this way. We're going to take this 1.02 that we multiplied 3 times by itself, and we're going to do just 1.02 to the third power. And again, we'll double check on the calculator, see that that works. So here's 1,000 times 1.02 raised to the power of 3, and over here you can see that that's what's going on, and we'll say equals, and sure enough 1061.21. Yay! So this also works. Now, the last thing we'll do is the thing that we always do as good algebra students. We will generalize. This is very specific. These numbers are for this specific problem, but we'd like to be able to calculate simple interest when we put money into a savings account, no matter what the interest rate and no matter what how many years and no matter what the initial deposit is. So we do something like this. Here's the final amount, Actually, if you want to see how it would have looked up here, it would have looked like this. This gets us the final amount. The initial amount we're going to call P, and I'll explain why in a minute. And then we always do 1 plus whatever the interest rate is. So 1 plus R, that's a little baby r. And then to the power of t, which is the amount of time. And let's go ahead and define all these. This is a formula that we're going to use, and I just wanted you to understand where it came from. My feeling is if you understand all the hard work that we could have done manually to get this answer, I'm hopeful that you really appreciate that this formula does all that stuff for us. And just imagine if we had to do this for 5 years or 10 years or 20 years, God forbid. This really makes our life easier. So in this formula, we have A is equal to, oh, hold on. A is equal to the final amount. That's one way to look at it. When we talk about things like radioactive decay, we will certainly refer to the final amount. But in terms of finance, this is what they call, the reason why we use A is because it's called the accrued amount. Accrued. It's not crude, it's accrued. You can go ahead and Google that, look that up in the Merriam-Webster dictionary and see for yourself. The other thing, the P stands for the initial amount. Again, when we talk about radioactive substances, we're concerned about initial and final amount. And again, for finance folks, P stands for principal. That is the word that's used for the initial amount. And then the next thing is little r is equal to the interest rate. And that is expressed, you will usually take the percent and convert to decimal. And if that is something you are bad at, then maybe it would not be a bad idea to work on that. And then finally, t is equal to time. And in this case, time is expressed in years. However, you could have an exponential function like this where the t is actually not years, where it could be minutes or seconds or almost anything that you want. It just depends on how quickly something is growing. In our case, the thing is growing once a year, and so therefore it makes sense to put t in years. One other thing that I'd like to end this video with is the idea that this particular type of function has a name. Because the amount of money is growing, we call this guy exponential growth. That is the concept here, exponential growth.